Alright, here's the video guide for lesson 10.3.2. 10.3.1 put us on to different combinations, and we were talking kind of about how many different ways can you combine certain letters, or how many ways can you arrange certain letters without them repeating. And we're going to continue that today with the idea of permutations, which is a specific way of arrangements. And we'll learn more about that right in the beginning with some definition stuff. We are going to do 121, 122, 123, and 124 here today. And we'll get right into it so we can figure out what this word permutations means. Okay, there are many kinds of counting problems, kind of like where we started last week, Thursday. In this lesson, we are going to learn to recognize problems that involve arrangements. In some cases, outcomes will be repeated, but in others they will not. A list of permutations includes different arrangements of distinct objects chosen from a set of objects. So we're talking about different arrangements, but they're going to have to follow some kind of special pattern for it to be called a permutation. In other words, permutations are arrangements of elements without using any element more than once and without repetition. As you work on the problems in the lesson, discuss these following questions. We can take a look at those, but really we're going to be focusing on the pattern here today, and we're going to see it quickly with this first problem. And so Jasper finally managed to save enough money to open a savings account at the credit union. When he went in to open the account manager told him he needed to select a 4-digit PIN, personal identification number. I forgot that's what that meant. Kind of cool. She also said that he could not repeat a digit. Right there is telling me that fact that it cannot repeat is a really big giveaway that this is going to be a permutations problem. All right, but that he could use any of the digits 0 through 9 for any place in his 4-digit PIN. Okay, so the first problem here, how many different pins are possible? And I'm going to do a decision chart like we saw last week. Okay, and so we're looking at A. We have a 4-digit PIN, which means we have 4 decisions. All right, we have a decision for what the first one's going to be. We have a decision for what the second number is going to be, and for the third and fourth as well. All right, now when we have that first PIN, we have numbers 0 through 9 that we can choose from. If I really listed out numbers 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, you would notice there that there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers to choose from because we're including 0. All right, and so on that first decision, we have 10 choices we can make. All right, now say we selected 0 to be the first number. Well, now we can't repeat that number, and so for the second decision, we only have 9. Right, because say we chose 0, now 0's off the list, we only have 9 decisions we could, or 9 choices we could do for that second decision. Say on that second decision we choose a number like 1, so now 1 is gone, so that means in the third decision we only have 8 choices. Fourth decision, say we chose 2 for the third one, now we only have 7 choices. Alright, so we see that decline like we did actually in a couple problems last week Thursday. You see that slow decline here, 10, 9, 8, 7, and for a decision chart, we just want to multiply across. So 10 times 9 times 8 times 7. And if we do this here, 10 times 9 times 8 times 7. I got to bring up my calculator very quickly here. We get 10 times 9 times 8 times 7, a number 5,040 possible pin combinations, in this case that they cannot repeat. All right, so that's your answer to part A is 5,040. Notice that the decision chart from this problem looks like the beginning of 10 factorial. Remember 10 factorial, or what a factorial is? 10 factorial, what that's equal to is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 10 factorial written out. So what they're saying here is notice that the decision chart looks like the beginning of that because our decision chart looks like, if I cross this part out right here, that's what our decision chart looks like, 10 times 9 times 8 times 7. Okay? But it does not go down to 1, so factorials could actually be used to represent this problem, but you must compensate for the factors that you do not use. So you could write 10 times 9 times 8 times 7, you could write that as 10 factorial over 6 factorial, and this is why. All right, so it says to discuss as a team, but this is why you can write it like that. And really, I'm just going to show you by crossing numbers out. So I'm going to write out 10 factorial over 6 factorial. I'm going to write it out like multiplication. So I'm going to write 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I'm going to write out 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. All right. Now, if the number is on top and the numbers are on bottom, we're allowed to cross them off because this is multiplication. So the 6 cancels, 5 cancels, 4 cancels, 3 cancels, 2 cancels, and 1 cancels. All right. Which, after the cancellation here, after this cancellation, we just get 10 times 9 times 8 times 7, which is what we saw in this decision chart up here. And so that is why we could write 10 factorial over 6 factorial and get that same answer as we did in our decision chart. And we're going to investigate that a little bit more in a later problem. All right, we'll move on to 10-22 though. With your team, discuss how you could use factorials to represent each of the following situations, then find the solution. 4 of the 5 problems involve permutations and 1 does not. As you work, discuss with your team which problems fit the definition for permutation and why or why not. Write your answers both as a factorial and as a whole number. Okay, I'm going to do some decision chart stuff and then probably write it as a factorial afterwards because it just helps me see that. So the first one here, 52 contestants entered a contest for a new school logo design. In how many different ways can the judges pick the best logo, the runner-up, runner-up 1, 2, and 3? And so really, we have a lot of problems here, but that's okay. In part A here, we are going to have 4 decisions to make. We are going to have a best logo, we're going to have runner-up 1, we're going to have runner-up 2, and runner-up 3, and so we're going to have 4 decisions to make, and we have 52 contestants. All right. Well, you can't have repetition here because you can't pick a contestant to be the best and pick that same contestant to be the runner-up 1. So right there's no repetition, which leads me to think that this is going to be a permutation problem. And the fact that order matters, that there is a best, a runner-up 1, a runner-up 2, and a runner-up 3. That order and that lack of repetition really makes me think that this is going to be a permutation problem. In fact, I think I can just come out and say that this is a permutation problem here for part A. If I make my decision chart here, I got first place, I got second place or runner-up 1, I got third place, and I got fourth place. All right. When you're talking about picking somebody for first place, there's 52 options because there's 52 contestants. They all got a chance to get first place. After somebody gets first place, you only have 51 options. After third place, you only have 50 options. And after you've picked your third place, you have 49 options. In a decision chart, we multiply through. And so we get 52 times 51 times 50 times 49. Sorry for the bad handwriting there. And that gives me, I'm going to grab my calculator quick. 52 times 51 times 50 times 49 gives you 6,497,000. So 6,497,400 different options or different ways that these contestants could take first, second, third, or fourth place. All right, so that's part of my answer there. The other part of my answer is to write this as a factorial. And how I'm going to do this is similar to what I did down here, or on this previous problem. They did 10 factorial over 6 factorial because that 6 factorial on the bottom canceled out all the rest. All right, and what this would be on this problem would be equal to 52 factorial on top from all the 52 contestants, but now we want everything 48 and below to be canceled, right? Because if we're looking at that decision chart, we have 52, 51, 50, 49, and really 52 factorial would go all the way down to 1. And so we want to cancel everything else that would carry on from there, which everything that would go from there would be 48 factorial. And so 52 factorial divided by 48 factorial should give you the same answer as this right up here. And if you want to check that, plug that into your calculator. And you should have on your calculator, and I know if you use the Google calculator, you can find it. You should have 52 and then that exclamation point, and then you just divide that by 48 times the exclamation point, or 48 exclamation point, and that should be the factorials. All right, I'm going to keep moving here because we got quite a few more problems to go. So we have the volleyball team is sponsoring a mixed doubles sand court volleyball tournament, and have 16 pairs have signed up for a chance to win one of the 7 trophies and a cash prize. And how many different ways can the teams finish in the top 7 slots? Okay, so there's 16 teams here that are signing up, and then there are 7 decisions to be made for the first 1 through 7 top slots. All right, and so we have, again, a permutation problem because you can't have somebody winning first place and second place or first place and third place. So there is no repetition that can happen, which is, again, a big sign that this is going to be permutations. And also the fact that order matters. The fact that there is a first place, there's a second place, there's a third place, there's a fourth place. The fact that there's an order to that also tells me that this is a permutation problem. All right, and so when we do the problem for part B, we have 7 decisions this time, which is quite a bit. We have first place, second place, third place, fourth, fifth, sixth, and seventh. All right. First place, there is 16 teams that could take first place. After somebody takes first place, that only leaves 15, then 14, then 13, then 12, then 11, and then 10. All right. And if this is a decision chart, we multiply through. So 16 times 15 times 14 times 13 times 12 times 11 times 10. This is going to be a pretty big number. 16 times 15 times 14 times 13 times 12 times 11 times 10 gives you an answer. I got to bring up my calculator. I wonder if it's going to be bigger or smaller than the first one. 16 times 15 times 14 times 13 times 12 times 11 times 10. Oof. All right. So that gives me 57,657,600 different ways that those teams could finish 1 through 7. All right. Now, if I want to write that as a factorial, what I have is on top, it's going to be 16 factorial. Oops. On top for my factorial, it's going to be 16 factorial. And I always get that because I'm looking up here and it looks like 16 factorial, just like it said in problem number 1. It looks like 16 factorial, but it stops at 10. All right, which means everything 9 and down, so like 9 times 8 times 7 times 6 times 5, everything from there got canceled, which means this is 16 factorial over 9 factorial. Because 9 factorial is pretty much canceled out of that decision, out of that decision chart. And again, if you want to try that on your calculator, it should give you that same number there. I'm even going to check it myself on this one. 16 factorial divided by 9 factorial does, in fact, give you the answer. Okay. We have about a minute in this one left. And so what I think I will do is I will just pick this up in a second video. I will do C, D, and E. I'll probably do 123. I'll see if I can get 124, but this might be a 3-video type of day, which I apologize for, but the more we actually work through this exploration, the better we're going to understand it. So pick up here at problem C, or at part C in the second video.